Hi and Assalamualaikum everyone. We are from Group O for assignment is SIC1009 Physical Chemistry. So these are the group members: Nur Shahada, the group leader; Aisha Maira, Nurul Ain Najiha, Nur Izzatul Shazwina, Nur Shuhada, Haris Najmi, Gerald Hobart, and Kavirat. So today, my friends and I will bring you to explore more about supercapacitors, which I strongly believe that all of us know that supercapacitors is the high power storage device that sit between traditional capacitors and also batteries. We specially brought to you with this two section, which are the secret life of supercapacitors and supercapacitors power beyond limit. These two sections will serve as mind-blowing facts about our main topic for today, which is supercapacitors. Without further ado, let's dive into the first chapter. What is a supercapacitor? Based on the slide, it says that a supercapacitor, also called as an ultracapacitor, is a special kind of energy storage. It has a huge power burst which can charge or discharge energy in seconds and has a very long lifespan, and it also applies a very good reliability and safety with no risky chemicals that can explode or leak. But don't worry all, I will not only read in the slide, but I will explain to you one by one. For your information, supercapacitor stores energy electrostatically, offering rapid charge or discharge, long cycle life, and also higher power density. So I would like to emphasize these 3 points in the slide to the three key benefits, which are fast charging, long lifespan, and also high power material. Fast charging, which shows it can be charged in seconds instead of minutes. Long lifespan, which shows it can last for thousands of cycles, and also high power material that ideal for bursts of energy. Next, let's move on to the components of view. First of all, we have electrodes and collector, electrolyte, and also separator. But what are the reasons behind having this component? So first, electrode and collector is a conductive material that holds the charge. Electrolyte is the medium that moves the ion. We will dive deeper shortly in the table below. And also separator that keeps the electrodes apart while allowing ion flow. Next, let's deep dive to the electrolyte part. So we include to you 3 types of electrolyte, which are aqueous electrolyte, organic electrolyte, and also ionic liquids electrolyte. Aqueous electrolytes such as H2SO4 and POH serve the very high conductivity but limited to -1 V per cell. Organic electrolytes such as acetonitrile and propylene carbonate supports higher voltage, which can be said as better energy density for commercial cells. And last but not least, we have the ionic liquid, which refers to any specialized salts, is excellent for high voltage and also high temperature environments, which can be said also as an electrolyte that's stable for harsh conditions. We move to the next slide.
Okay, so I'm going to briefly cover the 3 main types of supercapacitors, which are EDLCs, pseudocapacitors, and hybrid capacitors. EDLCs are the simplest. They store energy electrostatically, meaning they physically absorb ions onto the high surface area of activated carbon to form a double layer. They are known for excellent cycle life and high power density, but they have the lowest energy density. Pseudocapacitors use a fast, reversible Faraday redox reaction on the surface of the electrode materials, usually transition metals oxide like ruthenium and manganese oxide. This chemical change allows them to offer much higher specific capacitance and energy density than EDLCs, but they generally have a lower power density and a shorter cycle life. Finally, hybrid capacitors combine the best of both worlds. They typically use 2 dissimilar electrodes, one non-Faraday like carbon and one Faraday like a metal oxide. It's engineered to leverage the high power density of EDLCs and the high energy densities of pseudocapacitors. So next.
Who invented the supercapacitor? The supercapacitor we know today is the result of several key developments. The earliest patent dates back to 1957 when H.I. Baker of General Electric invented an electrochemical capacitor device using porous carbon electrodes. However, the underlying mechanism was not fully understood and the device was not practical for the commercial use at the time. The practical design is often attributed to Robert Meyer, a chemist at Ohio, who detailed a functional carbon double layer capacitor design in his patent filed in 1962 and awarded in 1966. Although some sources also credit Stanley Whittingham in the 70s, the trade name supercapacitor was officially introduced in 1978 when Japanese company NEC commercialized the Sohayo technology for the computer memory backup.
Now I'm going to talk about how the supercapacitor works. It all starts with storing an electric charge. Unlike the batteries, supercapacitor do this through a simple electrostatic force with no complex chemical changes. When you apply voltage, the positive and negative ion inside the supercapacitor will instantly gather at the electrode surface. This creates what's called an electric double layer. The ion form one layer on the electrode and the another layer in the electrolyte, which allow them to hold a massive amount of charge on the surface. Then, when you need the power, for example, when connected to a load, the supercapacitor discharges rapidly. The ions simply dissolve and return to the electrolyte, releasing all that stored energy. In short, they store charge statically in the double layer and release it on demand with incredible speed.
Alright, so now I'm going to explain about how long can supercapacitor hold its charge. In general, supercapacitor can only hold its charge for only a few seconds, or minutes, or even a week, depending on the material it uses. And supercapacitors store its charge through electrostatic double-layer capacitance and pseudocapacitance. Supercapacitors tend to lose their charge relatively quicker than battery because supercapacitor use carbon-based electrode and organic electrolytes, which promotes the higher self-discharge rate. So in this third point, I'm going to explain a bit about this point. Most supercapacitors are made out of porous carbon material and commonly used in double-layer capacitor. Due to the immense surface area, the ion absorption is relatively high and amount of charge stored per volt are also high. However, surface functionalities and impurities that present in the carbon can lead to higher self-discharge rate. And organic electrolytes allow for the wider voltage range, increasing energy density but typically have lower ionic conductivity and sensitive to moisture contamination. And this accelerates degradation and self-discharge. Therefore, supercapacitors are excellent for short-term energy storage and rapid charge, but not designed for long-period charging, as it has high self-discharge rate. Yeah, next slide.
Now, here are some advantages and disadvantages of using supercapacitors. The first advantage is that supercapacitors have a higher power density compared to normal batteries. They use activated carbon material to increase the capacitance value so that a large amount of power can be quickly delivered. Next, supercapacitors have a high charging rate, meaning they have the ability to charge and discharge rapidly to support quick bursts of energy. On top of that, supercapacitors also have a longer cycle life than normal batteries. They can undergo millions of charging and discharging cycles without causing a notable degradation. On the other hand, supercapacitors also possess a few downsides. As opposed to having a high power density, supercapacitors have a much lower energy density than normal batteries. They store less energy per unit volume due to limited surface area of electrode that is used as charge storage. Next, supercapacitors are unsuitable for AC circuits. Supercapacitors cannot maintain a high charge state as voltage changes frequently in AC circuits. And lastly, supercapacitors have high self-discharge rate. They discharge more frequent than normal batteries due to their low internal resistance.
When it comes to choosing our power sources, batteries and capacitors go against each other. Batteries come in strong with their high energy density, storing loads of power for long-term use and delivering steady, reliable voltage as they discharge, making them perfect for devices that need endurance. Capacitors, on the other hand, are quick but not built for the long haul. They store much less energy, lose voltage rapidly, and need constant recharging to stay in the game. While supercapacitors can stay more than traditional capacitors, they still can compete with the energy capacity of batteries. And now we will move to the next slide.
So now let's move to major applications of supercapacitors. What are they used for? First, GSM and toy applications. In toys, supercapacitors are built to last for 10 years or over 100,000 cycles, as they deliver high power while not overheat easily, and they are safer than batteries. In GSM, supercapacitors play a vital part in reducing voltage drops in mobile phones, leading to low probability for voltage to reach critical level and extend operation time. Next, in IC memories and microcomputers, supercapacitors are widely used as maintenance-free power sources, as they do not degrade chemically and do not need electrolyte replacement. They also have large lifespan due to their ability to operate over wide temperatures. Other than that, supercapacitors are also crucial for electrical and mechanical systems. In quality power requirements for uninterruptible power supply installations, in load leveling, for electric and hybrid vehicles, traction domains, and engine. They provide intense power bursts, high current, while ensuring safety, such as regenerative braking and smooth out voltage fluctuations. While in telecommunications, they provide emergency backup during power outage. Fun fact, our first prototype vehicle in April 1997, Blue Angel, can recover energy during break using supercapacitors. Supercapacitors are also used for other domains, such as radars and torpedoes in the military domain, defibrillators and cardiac pacemakers in medicinal, and laser and welding in the industry. Next, let's move to our second topic, which is the most fun topic, supercapacitors, power beyond limit.
Supercapacitors are revolutionizing energy storage, achieving instantaneous charging through their unique mechanism. Their core benefits stem from three key points. First, the fundamental difference is electrostatic energy storage. Unlike batteries, which rely on slow chemical reactions, supercapacitors use a non-Faraday process on their electrode surface. This purely electrostatic process allows for the almost instantaneous movement of ions, which is the secret to repeat energy transfer. Second, they offer high power density. This means they can handle very high current during charging and discharging without overheating and degrading for their components. This is critical because a conventional battery would suffer a significant lifespan reduction if subjected to these high charging rates. Finally, they boast exceptional durability. Supercapacitors can endure hundreds of thousands to millions of cycles with no significant capacity loss, making them the ideal technology for applications that require frequent rapid top-ups.
Supercapacitors in space are like the secret power-up boosters that keep satellites running smoothly. They stabilize a satellite's power supply during big events like firing thrusters or moving through eclipse transitions, making sure nothing flickers or fails. They also regulate the power bus by absorbing sudden high current demands, protecting the system from voltage spikes like a cosmic shock absorber. In emergency situations, supercapacitors can jump-start thruster quickly for collision avoidance maneuvers. No long warm-up needed. And for instruments like synthetic aperture radar, which fire rapid high power pulse trains, supercapacitors supply the burst energy needed to keep those imaging systems sharp and reliable. In short, supercapacitors are the space heroes, quietly powering in the most exciting moments in orbit.
In this part, I'm going to explain how the supercapacitors can shrink into wearable size. Unconsciously, supercapacitor can be found in wearable devices, and most popular wearables are smartwatch and fitness band. Firstly, wearable device like smartwatch use stretchable fiber-based supercapacitor that's stored in it. As we know, the function of supercapacitor is to store charge. This fiber-based supercapacitor is suitable for wearable like smartwatch because it has a characteristic of lightweight, flexible, and have high energy density, which more convenience for it. With these characteristics, wearable like smartwatch can easily store in charge because of presence of fiber-based supercapacitor. The textile supercapacitor, or TLCS, is one of the supercapacitor that is still gaining attention these days. Textile supercapacitor can be applied in some products such as smart clothes or smart shoes, since both of these products are made out of textile. Textile supercapacitor emphasizes the sustainability of textile and give us significant properties such as lightweight to be worn and its compatibility with wearable microelectric devices. However, the products that use textile supercapacitor are still in an early adopter stages, and some of the brands that produce textile-based supercapacitor include Hexoskit and Cute Circuit. And there's still one more supercapacitor that are most promising and popular research materials today, which is graphene supercapacitor, or known as flexible thin film graphene supercapacitor. Graphene supercapacitor are highly suitable for wearable electronics since they own a characteristic of flexibility, lightweight, conductive, and can be integrated into film, such as polyamide or fabrics in the form of coating. Plus, graphene supercapacitors are foldable and bendable, which can improve the space efficiency in the wearable and allow energy storage layer to be transferred into strap or outer case of wearables. Next slide.
Now, let's start with the mystery of quantum capacitance. The classical capacitance of supercapacitors are based on principle of electric double layer capacitance (EDLC) and pseudo-capacitance, which use special electrodes such as activated carbon to increase the capacitance. In classical, we assume the electrodes can accept any amount of charge without resistance, but quantum capacitance only allows electrons to occupy energy states available when extra charges are added. It occurs due to amount of quantum states available for electrons exist. What is quantum capacitance? Quantum capacitance is capacitance which arises due to measure of ability of the quantum states to accept additional charge. If there are only few quantum states available, which means low density of states, charge can't be added more as there are no seat for electrons to occupy and vice versa. The factors of low density of states are the use of semiconductors and insulators, where only small and almost zero amount of free electrons are occupied, while density of state is almost zero and doping shifts to p-type, which means they remove more electrons at Fermi level when graphene is used. Fermi level is the highest energy level electrons can occupy at absolute zero temperature, while the factors of high DOS is the use of metals due to many free electrons can occupy. Many energy levels are available near Fermi level. Flat bands accumulate many states at one energy and doping shifts to n-type at Fermi level. Hence, quantum states and electrodes' internal electronic structure becomes the limit towards capacitance of supercapacitors. Even if the EDLC are large, small quantum capacitance will reduce total capacitance. Let's move to the next slide.
Self-healing supercapacitors made from biomaterials. Creating a supercapacitor that can repair itself self-healing has become a reality thanks to natural biomaterials. The first biomaterial is alginate or sodium alginate, a polysaccharide extracted from brown seaweed which is non-toxic, biocompatible and highly flexible. Its self-healing mechanism relies on the formation of reversible ionic bonds with calcium ions, allowing the structure to break when damaged and automatically reform, acting like a chemical velcro. Additionally, seed fibrin, SF, a protein derived from seed fibers, is employed. SF is known for its superior mechanical strength and high biocompatibility, making it an ideal material to utilize on electrode binders and for device and encapsulation layers.
Now, we have reached the end of our presentation, and that's all from us. Thank you for listening and have a good day from Group 2.
Bye.
Bye!